In the second part of the lecture about refraction of light, I will discuss the lens equation and the parameters that determine the image generated by a lens. When discussing the lens equation and figuring out the parameters that determine the image produced by a lens, we need to know the following features of the object, lens, and image system. So first, the object is placed a distance from the lens, and this distance we label it S. The focal distance of the lens is F, and the distance that the image is from the lens we are going to label it S prime. So F is the focal distance of the lens, S is the distance from the object to the lens, and S prime is the distance from the image to the lens. Then in terms of those parameters, the lens equation reads that 1 over the object distance to the lens plus 1 over the image distance to the lens is equal to 1 divided by the focal distance of the lens. The magnification of the lens, M, is given as minus the ratio of the image distance to the lens and the object distance to the lens. Now, there are several rules that must be observed when calculating the parameters of the image generated by a lens using the lens equation and also the magnification formula. Let's list those rules. Here are the rules for the focal distance, the image distance, and the object and the magnification of the lens. So when calculating with the lens equation, the focal distance is selected to be positive number for a converging lens and a negative number for a diverging lens. The distance between the image and the lens is positive if the image is on the far side of the lens and real. The image distance is negative if the image is on the near side of the lens and virtual. The far side of the lens is the side of the lens opposite to the side where the object is. And the near side of the lens is the same side of the lens where the object is. So those two rules mean that if the image distance is a positive number, then the image is on the far side, as I already said, but also it means that the image is real. In other words, if we place a screen on the far side of the lens, we will be able to see the image of the object on that screen. When the image distance is a negative number, then that means that the image is on the same side of the lens as the object. So if we place a screen there, we are actually not going to be able to see the image because the screen will block the light from the object, so that light is not going to actually pass through the lens. Because of that, the image is virtual. The rules for the magnification of a lens are the magnification, if it's a positive number, then the image is erect, and if it's a negative number, then the image is inverted. So let's show two example calculations using the lens equation. A 10 centimeter object is placed in front of a diverging lens 60 centimeters from it. If the focal length of the lens is 30 centimeters, find the magnification of the lens, the size of the image, and whether the image is real or virtual, and inverted or erect. So let's make a list of the parameters stated in the problem. So the object distance is 60 centimeters, the focal distance is 30 centimeters, and this is a diverging lens. So in order to find the magnification, which is equal to the ratio of the image distance to the object distance, I need to find the image distance. So for that purpose, I need to use the lens equation. 1 divided by the object distance plus 1 divided by the image distance is equal to 1 divided by the focal distance. So from the rules of the lens equation for the focal distance and the image distance, since this is a diverging lens, the focal distance must be entered with a negative sign. So then the lens equation is written as 1 divided by 60 centimeters plus 1 divided by s prime is equal to 1 divided by minus 30 centimeters. So from here, I'm looking for s prime. So that means that I will move 1 over 6 centimeters on the right side of the equation. So from here we get that 1 divided by s prime is equal to negative 1 over 30 centimeters minus 1 over 60 centimeters. After finding the common denominator here, which is 60 centimeters, that becomes minus 2 minus 1 divided by 60 centimeters, or in other words, this is minus 1 divided by 20 centimeters. So from here, solving for s prime, we get that the image distance is negative 20 centimeters. Now, what does this number mean? We can decipher by looking at the rules for the lens equation. The image distance is a negative number if the image is on the near side of the lens and also virtual. So this means that the image is 20 centimeters from the lens on the near side, which means on the same side as the object, and is virtual. So the image is on the near side of the lens, 20 centimeters from the lens, and is virtual. Now let's calculate the magnification of the lens. The magnification of the lens is calculated as minus the ratio of the image distance to the object distance. So that is minus 20 centimeters divided by 60 centimeters. So the image, not the image, but the lens magnification is 1/3. Since the magnification is a positive number, from the rules that I listed a few slides ago, that means that the image is erect. So the magnification is a positive number, which means that the image is erect. Now let's calculate the image size. The image size is simply equal to the object size times the magnification m. So that is 10 centimeters times 1/3, or this is 3.3 centimeters. So the image is smaller than the object. Let's do one more example. The focal length of a converging lens is 40 centimeters. If an object is placed 60 centimeters from the lens, find the position of the image. If the object is 10 centimeters, what is the size of the image? So the focal length of the lens is 40 centimeters. The object distance is 60 centimeters. This is a converging lens, which means that in the lens equation, we must take the focal distance with a positive sign. Since the question is to find the size of the image, that means that I must calculate the magnification of the lens. The magnification of the lens requires us to know the image distance. In order to find the image distance, I need to use the lens equation. So let's solve the lens equation for the image distance. So the lens equation, when substituting the parameters given in the problem, becomes 1 divided by 60 centimeters plus 1 over s prime is equal to 1 divided by 40 centimeters. From here, 1 divided by s prime is equal to 1 over 40 centimeters minus 1 over 60 centimeters. Let's find the common denominator of those two fractions, that is 120 centimeters. So we get 3 minus 2 divided by 120 centimeters. Or in other words, this is 1 over 120 centimeters. So from here, the image distance is 120 centimeters. So this is a positive number, and according to the rules for the lens equation, that means that the image is on the far side of the lens. So that means behind the lens, or the opposite side of the lens from where the object is. And the image is real. So again, the image is located on the far side of the lens, and it is real. Now let's calculate the magnification of the lens. The magnification of the lens is minus 120 centimeters divided by 60 centimeters, that's minus 2. Since the magnification is a negative number, according to the rules for the magnification, that means that the image is inverted. Now let's calculate the size of the image. So the magnification of minus 2 tells us that the image is going to be twice the size of the object. So calculating that gives us that the image is 20 centimeters in size, and the minus sign again just means that the image is inverted. And so solving the lens equation is a very straightforward process as long as you follow the rules detailed in the explanation or definition of the lens equation. And with this, I'm going to conclude the discussion on refraction of light.